Okay, so welcome to Math 408, L functions and sphere packing, lecture 12, October 14, 2020. So what I want to do today is continue our conversations on Fourier series leading up to, hopefully, Poisson summation, almost surely not this lecture, but hopefully the one after that. There will not be class on Friday. I will email what's going on. I have posted two formulas on the board which are going to be extremely useful later. I debated putting them on a sideboard and just moving the camera for one moment, but they are so important they need to be kept up for the whole lecture. But they don't take up too much space if you write them out like this, so I'll just sacrifice a little bit of board space. So a little bit of notation. So E and X is shorthand for E to the 2 pi I and X. And we've been using, f hat of n is the integral of f of x e to the negative 2 pi I and x dx from 0 to 1. And we will assume our function f is periodic. And even though it should be obvious its period is going to be 1 since we're doing everything from 0 to 1, I will explicitly say it's periodic with period form. And we talked a little bit about what to do if your function is not initially periodic, how you can extend it like that. The whole goal is to try to approximate a function well by a series. And we've talked about Taylor series in the past. You've seen that in calculus. We're using a new basis. We're using the basis of trigonometric polynomials. And the question is this complete? If I look at the infinite sum, does it approximate our function? And if the answer is no, and sadly the answer is sometimes no, for which functions will it do it? So I will go to my notes, which I'll simply upside down. There's some interesting results as to what can and cannot be done. And then, so the more conditions you assume about the function, not surprisingly, the more is going to be true. And so differentiability is going to be huge. So it is possible that the Fourier series of a continuous function diverges at a point, which is distressing. Kolmogorov in 1926 constructed a function whose L1 norm is finite, and the Fourier series diverges everywhere, even worse. But if your function is L2, so if it's the integral of its absolute value squared is finite, then the story is completely different. And in that case, Carlson proved that the Fourier series converges to the original function for almost all values of x. So L2 is a really good condition. One of the things I had you think about was when are your spaces contained in each other? When is L1 contained in L2? When is L2 contained in L1? I wrote two formulas on the board. The first is the Dirichlet kernel, dn of x, and it is the sum of e and x, n going from minus n to n. What kind of sum is this? It has a name. And I don't want finite sum. It is a sum you have seen before. If you want, I will rewrite it in a way to hopefully make it clear. I will write it as e1 of x to the nth power. What kind of sum is it? Not power series. There's a word I want, it's not power. Geometric. It's a geometric series. So by the geometric series formula, we should be able to get this. So there will be a homework assignment, and I will send it, that prove this. This is one of the standard problems. Use the geometric series and prove the following. Then we have the Fejer kernel, which is 1 over n, sum n goes from 0 to n minus 1, dn of x. So it's basically an average of the Dirichlet kernels. Do you want to try to sum ratios of signs directly? Hell no. You'd much rather work with exponentials again and just have a bunch of geometric series that you somehow combine. And so this is another identity to just show. Now these functions have some interesting properties. So one of the great things is what's called an approximation to the identity. And out of curiosity, how many of you have seen approximations to the identity before? Okay, no hands are going up. I'm curious as to what you did with Fourier series. Without this, it's one of the great concepts. It's essentially a way to mathematically deal with the Dirac delta functional legally. What's the Dirac delta functional? Well, the integral from minus infinity to infinity of f of x delta of x dx is just f of 0. Or more generally, if we replace this with delta of x minus a, we would replace that with f of a. You should view the delta functional as it has all of its mass at either the point 0 or a. So infinite density. This is not a great thing to work with, but if we think of it as an operation on functions, taking functions as input and giving us numbers as output, then it's perfectly well defined. You would say, delta of f is just f of 0. Or delta sub a of f would be f of a. And if we write it like that, then there's no problem. It's an operator. It takes functions as input. Okay, not a problem. We want to be able to use the integral notation, which is nice and friendly, which we've seen before. So we extend things a little bit. So an approximation to the identity has three properties. So an, well, I like doing lowercase n's better, is an approximation to the identity if the following hold. An of x is greater than or equal to 0. The integral of an of x dx equals 1. And for all epsilon greater than 0, why did you enter this way? Yeah. There exists a delta greater than 0 such that the integral of x greater than delta of an of x dx is greater than or equal to 1 minus epsilon. So I'm being a little bit vague in terms of, am I working on the interval 0, 1, negative a half, negative infinity, infinity? If I'm doing the interval 0, 1, I'm almost surely doing it by looking at a periodic function. So looking at the interval 0, 1 is the same as looking at the interval negative a half. And what this is essentially saying is, is this how I want to phrase this? I want to phrase it so that I can make as much of the mass as I want outside of so wait, I phrased this wrong. And you should be able to tell right now that I must have made a mistake here. So it's actually a really good mistake that I made. I made this mistake. So you should know these three properties can't be what I want for the sequence of an functions to be an approximation to the identity. Why does this have to be wrong?
Does it not integrate to 1?
Nope. But if you look at it, there has to be something wrong with what I've done. So I'm talking about a sequence an, right? Statement 1, an is greater than or equal to 0. Statement 2, an of x is equal to 1. Statement 3, for all epsilon, there exists a delta. There's no independence anywhere. There's nothing talking about it. I can just take the same n again and again and again. There's got to be a mistake here. And I'm just so used to epsilons and deltas, I just started to write things with epsilons and deltas. We're going to have epsilons and deltas in a moment. So it's for all delta, just make sure, for all delta greater than 0, we'll say delta less than a half, there exists an n naught such that, no, I'll just do it this way. The integral x greater than delta of an of x dx goes to 0 as n goes to infinity. And now I have some independence. And what this is saying is, here's minus a half, here's 0, here's some interval of size delta. As n gets very, very large, more and more of the mass is concentrated very close to 0. And the amount of the mass outside is getting smaller and smaller and smaller. We know it has to integrate to 1. And what this is saying is as n gets larger and larger and larger, more and more of the mass is concentrated. So the first question is, do such functions exist? Can you give me a sequence of functions an that would be an approximation to the identity? Well, pretending you are muted. Did you try to say something? I still can't hear you. Okay, there you go. Okay, now I can hear you. Okay. It was on my computer. Somehow it got muted after class. What did you say?
I was proposing getting a sequence of Gaussians in decreasing variance.
Good. So I'm going to do Gaussians as the third example. So Gaussians will be the third example. What's a simpler example?
Maybe like the characteristic function is an interval.
Yeah. So if we take, an of x, well, let's take a of x is minus a half, and so if we take this as our function, ax, that will clearly integrate to 1. And then we'll define an of x to be a of nx, and then n times that. And if you think about that, what does that mean? If it is going to be 1, I'm sorry, it's going to be n if the absolute value of x is less than or equal to n over 2. No, 1 over 2n. And 0 if the absolute value of x is greater than 1 over 2n. So essentially what we're doing is we start off with a function that is non-negative, integrates to 1, and then we modify that for each n. And we're essentially tightening it up. And so now, as we draw more and more, it's going to get tighter and tighter and tighter. Another one we could do, 0 minus a half would be the second choice. Second simplest example. Yeah, triangle, right? Triangle going all the way up to height 2. That'd be another good example to do. And if we try to integrate directly, if I integrate, minus infinity to infinity of f of x against an of x dx, this becomes just the integral. X goes from minus 1 over 2n to 1 over 2n times f of x times n dx. And if you think about it, if f is nice, I can write this as n, integral minus 1 over 2n to 1 over 2n f of 0 plus, say, f prime, maybe c of x times x dx. Some kind of Taylor expansion. And if we look at this now, we have an f of 0, an interval of size 1 over n times n. So the main term is going to be f of 0, and then plus something like big O means an error of size, like the maximum of f prime. And then when we integrate the x, we put in an absolute value, they'll become an x squared over 2. We'll get basically something of order 1 over n squared times n. It's going to be something of size n over n squared. And that's going to go to 0. And again, if you want, you could put in some kind of Taylor series here in terms of what the error is, but there's some point over here where it's f of 0 plus the first derivative value at some point. What theorem is that? So I'm basically saying f of x equals f of 0 plus f prime of some point c of x times x. Why is this true? Yeah, this is the mean value theorem. This is just f of x minus f of 0 over x minus 0 is f prime of c of x. It's just the mean value theorem. And so I do have such an approximation so long as f is differentiable. So if my function is differentiable and the first derivative is bounded, then it's going to converge to f of 0. At least it will converge if we use this choice. And the theorem is that as long as your function f is nice, it doesn't matter which approximation to the identity you use, they're all going to converge to f of 0. We could do the triangle, and then the last one that was suggested was Gaussian. So you would take a of x to be 1 over 2 pi e to the negative x squared over 2. That will integrate to 1. So how would we make the variance smaller? What would we want sigma to be?
You'd want it to go to 0. So you'd want it to be like 1 over n.
Yeah, so we could let a n of x, it's the exact same formula. It's just going to be n, a of n times x. And that would give you like an e to the negative n squared x squared over 2. And then you would have, oops, this should be a square root here. And you'd have a square root of 2 pi times 1 over n squared. And so once we have a function that's non-negative and integrates to 1, we can easily convert it to an approximation to the identity. The question is, which ones are easier to work with? Well, if I'm working with Gaussians, it's wonderful. It's infinitely differentiable. I'm not worried about anything. If I'm working with the triangle function, it's not differentiable at some points, square, similar problems as well. It turns out approximations to the identity have a number of tremendously valuable properties. So given that we have two sequences on the board, dn and fn, what is the question to ask? Bless you. So what's the first question we should be asking about dn and fn? I'm sorry? Well, what would you like to know about them? Are they
Continuous.
not continuous?
Differentiable.
Nope.
Inside R. Approximations.
Are they approximations to the identity? Right? Do you think they both are approximations to the identity, or does one of them give you some concern? Has to be non-negative, has to integrate to 1, and has to have the mass concentrated. So what's nice is we have two ways of looking at them. We have the sum term by term, and we also have these trig expressions. To see if it integrates to 1, well, every exponential integrates to 0 except the E0 term. Right? Because E0 is just 1. So this is going to integrate to 1. The only integral that matters is the n equals 0 term. If you look over here, each of the dn's integrates to 1. So I have n of them, I divide by n, it still integrates to 1. So this property is true for both. What about non-negative? Is non-negative true for both? What do you think?
Yeah,
Why yes?
because d of n or d sub n is never going to be negative. Right?
Okay, why will it never be negative?
Because the value of for ex, even like negative n is still going to be greater than 1.
No, because remember, e to the x is e to the 2 pi I nx. That's cosine 2 pi nx plus I sine. Well, we have the sum, but we also have the fact that it's sine of 2n plus 1 pi x over sine of pi x. Can you give me an x where this is negative? Sine itself alternates between positive and negative, right? The period of sine 2n plus 1 pi x is much shorter than the period of sine pi x. So when x is near 0, sine is near 0. When x is a small positive number, this is small and positive. This will be small and positive. Then the numerator will hit 0, and then the numerator will be negative, while the denominator is still positive. The Dirichlet kernel is not an approximation to the identity. It does integrate to 1. And I'll leave you to think about, does its mass concentrate? But the Dirichlet kernel is not as easy to work with as the Fejer kernel. Is the Fejer kernel non-negative? Yes, why?
Squared.
Yeah, you put it as squares. I debated writing this as the square root of n and then just having the whole thing squared. To just really drive home, this goes back to our famous inequality. If x is a real number, x squared is non-negative. Extremely valuable. So the Fejer kernels are going to be approximations to the identities. The Dirichlet kernels are not. And so it turns out the Fejer series has better convergence properties than the Dirichlet series. Now I'm already asking you, we're leading up to stuff that will be very useful for the sphere packing, some of these interpolation formulas. And we're going to need to approximate things. You've worked with Taylor series before. I'm trying to convince you to use Fourier series, and now I'm actually telling you, well, actually screw Fourier series, let's do Fejer series. Let's look and see what these are going to be. So if you've taken probability, you've seen convolutions. Did we mention them briefly in this class?
I think so.
I think so. So we'll say, f star g of x is the integral, say, minus infinity to infinity of f of x minus t g of t dt. And of course, instead of doing it from minus infinity to infinity, we could do it from minus a half to a half, just whatever interval we're looking at. And so, the better, more general way of writing this is just over the interval I that we care about. F star g is the same as g star f. If you think of f and g as densities of probability distributions, then it's really clear, because this is the density of x's random variable plus y's random variable, and addition is commutative. Let's look at dn star f of x. This is going to be the integral. I'll go from 0 to 1. And then I will do a sum and goes from minus n to n of e to the 2 pi I n x minus t f of t dt. What's the first thing you want to do when you see this expression?
X minus t, make it u.
I'm sorry?
Substitute.
So one is to do a u substitution. I claim that's not the first thing that you should be thinking of. We don't have that many tricks for multivariable calculus, and this really is a multivariable calculus.
Oh, Fubini. What's the
Fubini, flip the order. Can you flip it?
Is it going to be finite?
So if you put in absolute values, you will see that everything is finite, and you can't interchange. It really helps if this is a finite sum. So this is the same as the sum, n goes from minus n to n, integral from 0 to 1, f of t dt. But there's something else I want to do. I'm going to split the exponential. And we saw this when we did the chi-squared random variables. And we were talking about the area, the volume of a sphere or a hypersphere. Pull things out of the integrand if they don't depend on that variable. Get them out of the way. I will put the e to the 2 pi I and x here, and an e to the negative 2 pi I and t over here. Does this look like anything you've seen before? Yeah, it's the Fourier coefficient. So n goes from minus n to n, f hat of n, e to the 2 pi I n x. Well, that was just our finite Dirichlet series. And now we see an idea of why we might care about the Dirichlet convolution, the Dirichlet kernel. So we call this the Dirichlet kernel. And we see that if we convolve our function with the Dirichlet kernel, we actually get back the Fourier series. So here's a way to get your hands on the Fourier series. Now, let's look at what would happen if we did instead Fn convolved with f. I could go through the whole argument as before. Do we need to? Can you accept that this should just be 1 over n, the sum, n goes from 0 to n minus 1 of s little n of f?
Yeah, the integral doesn't.
The integral doesn't really matter. So that's one way to look at what we're going to have. We can expand this another way. And so we could look at what exactly is this Fejer sum. So Fn of x is the sum, 1 over n, little n goes from 0 to n minus 1, of dn of x. And that's going to be a sum, I'll go say maybe m goes from minus n to n of e sub m of x. All right, is that correct? I've expanded out what each dn of x is. And you would first take n equals 0, n equals 1, n equals 2, and so on, and so on, and so on. So let's think if there's a way to simplify this. When you look at this, if you look at the term E0, E1, E negative 1, E2, E negative 2, every term doesn't appear equally. Does E0 appear for every choice of little n? Yes, E0 always appears. So you have E0 big N times, you divide by n. So it's just going to be E0 of x. Now, how often does E1 occur? N minus 1. It occurs every time except for little n equals 0. And then we divide by n. So we're going to have plus a n minus 1 over n. And I'll do E1 of x plus E minus 1 of x. And I think the pattern is clear as to what happens as you go further and further down. So this is going to be the same as the sum. Little n goes from 0 to big N, 1 minus little n over n. I'm just trying to think how I want to do this. I'll have n go from minus n to n of e to the nx. So the E0 is going to occur every single time. E1 and E negative 1 occur almost every time. What we're really doing is we're tweaking the initial Dirichlet kernel. The initial Dirichlet kernel keeps this sum going from minus n to n, but replaces the n over here with infinity. So all we've done is we've slightly weighted things. All right. I'm going to assume everybody remembers that if we do the Dirichlet kernel, we get the Fourier series. I'm going to erase this, and now look a little bit more carefully. It's going to be a very similar calculation. What happens if we use the Fejer kernel? And one of the reasons I want to present the material the way I'm doing it is to just constantly emphasize how much your choice of how you look at the algebra impacts what you're able to observe. If you are stuck and things are not looking well, try to see if there's another way to view the algebra. So this was an initial way to do it. It's fine. But it's now giving us a sum of weighted Fourier series. If we use this expression, then we would have fn star f of x would be the integral from 0 to 1, the sum n goes from minus n to n, 1 minus n over n. Oh, oops, there's a small mistake here. What's the mistake? I need an absolute value here. E to the 2 pi I n x minus t f of t dt. Basically, it's the same calculation as before. We flip the sum in the integral. We'll have a sum, n goes from minus n to n, 1 minus absolute value of n over n. The e to the 2 pi I n negative t is going to give us f hat of n, e to the 2 pi I n x. And recall, Sn f of x is the sum, n goes from minus n to n, of f hat of n e to the 2 pi I n x. And so, to be extremely pedantic, I will put a 1 here. That's all we're doing. All we're doing is we're weighting the Fourier coefficients by this factor here. The general principle is mathematics, analysis, number theory. We like smooth weights rather than sharp weights. So here, the weight is 1, and then as soon as you get to n, plummets to 0. Here, the weight is slowly decaying in a triangle. So as long as little n is much less than big N, the weight is essentially 1. If little n is even going up to square root of n, you're not really seeing that much of a difference from the weight. But as n starts getting comparable to n, those coefficients get smaller and smaller weights attached to them. Until in the end, it's insignificant. So this is a better way over here of representing the Fejer series to see what it's doing. The impact is to give us a weighted Fourier series. So it's a weighted questions on what we've done up till now? So we've got our approximations to the identity. We've seen how if we use convolutions, the Dirichlet kernel leads to the standard Fourier series, the Fejer kernel leads to the weighted Fourier series. And just because I don't think I've actually put his name on, there is an accent over the E. Okay. Now that we have this, what question would you like to ask about this, the Dirichlet, the Fourier series and the weighted Fourier series? So what would you hope? So one is that they would be the same, or at least the same in the limit as n goes to infinity. But what question would you ask relative to the original function? Do they approximate? One of the choices you have in math is how generally do you want to prove a theorem? If you can prove something in great generality, then you can just say, aha, the conditions are met, therefore it's true. We could try to prove how well the Fejer series approximates a function, but the Fejer series is coming from the Fejer kernel, which is coming from what? What property does that sequence have? It's a so those functions Fn, what are they? They're an approximation to the identity. So we should try to prove a result about approximations to the identity. And if that's true, then it will be immediately true for the weighted Fourier series. Because the weighted Fourier series is just a special case. So if you could choose the laws of math, what would the derivative of a product be? Product of the derivatives. And the derivative of a quotient would be the quotient of the derivatives. No way you're getting that. If you want your function, say your Fejer series to converge to your function f, what do you think is the minimum ante that this function needs to have for you to have a hope of talking about convergence? Your function f should be so if you want your Fejer series to converge at every point, continuous. If your function is not continuous, then it seems very hard to hope that one of these series will converge to it when the function itself is not even converging. So in terms of what assumptions do we need, let's assume f is continuous. F is continuous. An is an approximation to the identity. Then An star f converges to f pointwise. And we can talk in a little bit about exactly what do we mean by that convergence. But if I don't assume that my function is continuous, it seems unlikely to be able to get anything like this. If we can prove this about any approximation to the identity, then we should be good with the weighted Fourier series because the Fejer kernel is coming from an approximation to the identity. All right, so proof. And this is one of the most famous types of proofs in real analysis. It has a specific name. Let's consider An star f of x minus f of x. Well, we know what An star of f is. This is just the integral. Let's do things some. I'll do minus a half to a half of An of x minus t f of t dt minus f of x. If you look at it, doesn't it look like f of x is being left out of the fun? f of t gets to be integrated. Poor f of x is not being integrated. Is there anything we could multiply it by that would make it look like an integral? I want an integral involving t. What could I put in there? Well, you know what the value of the integral has to be. I'm sorry?
Well, we know the integrals of all ans.
Yeah.
T go to 1.
So let's put an an of t. We've just multiplied by 1, one of our most valuable tricks. So this is now the same as the integral from minus a half to a half of an of x minus t f of t minus an of t dt. Oops, sorry. F of x. When you look at this, is this how we want to do things? So what should we change? See, this is an an evaluated t. This is an an evaluated x minus t. Well, an star f is the same as f star an, right? And if we do it that way, then this would become an an of t, and that would become an f of x minus t. Oh, that looks much nicer. And again, it's all about doing the algebra. And now if we look at what we have the integral from minus a half to a half, and we'll have f of x minus t minus f of x, and then we'll have an of t dt. And we want to show this is small. If we're lucky, we want to show it's uniformly small. And so we break this up into 3 intervals. The integral from minus delta to delta of f of x minus t minus f of x an of t, plus the integral from delta to 1/2, plus the integral from minus 1/2 to minus delta of f of x minus t minus f of x an of t dt. And given that class is almost done, we can finally erase all of our stuff here. So we have 3 integrals. This is going to be one of the famous 3 epsilon proofs. So have you seen 3 epsilon proofs in analysis? Almost just a bunch of results. If you want to hold your head up high as a real analyst, you choose things so at the end of the day, you get it's less than epsilon.
Yeah.
If you don't give a shit, you might have 13 epsilon over 7. And say, but since epsilon is arbitrary, I can let epsilon equal 7/13 epsilon prime, and now I have it less than epsilon prime. And so a lot of times people just say, we get it less than 3 epsilon. If you want to think a little bit, you would want to make each one of these less than epsilon over 3. I don't really care which one you do. So we have 3 integrals. Because f is continuous, implies f is uniformly continuous. Okay, that should make you a little concerned. What do I need for uniform continuity now?
That for all x greater, or, no, that there's some n such that when n greater than n,
Well, this,
you want them to all go to f of X.
So what you want is, in the definition of continuity, you don't want delta to depend on x.
Yes.
So uniform continuity is, given an epsilon, there is a delta that works simultaneously for all x. It is very important now that I'm on a finite interval. And so here, it's now necessary. So now we are using finite interval. So I'll let you think as to whether or not the thing would be true if we did not have a finite interval. And what would be necessary? Now, I only claim that it converges pointwise. I'm trying to get good convergence everywhere. So if you only want to do pointwise convergence, you don't need a finite interval. But if you want to have the same convergence everywhere at the same time, now I want to use finite interval and I want to use uniform continuity. So by uniform continuity, I can make f of x minus t minus f of x in absolute value less than epsilon over 3 if the absolute value of t is less than delta. We have control over what delta we take. So if we take delta sufficiently small, by uniform continuity, this is at most epsilon over 3. Because an of t is positive, the contribution of this piece is going to be at most epsilon 3 times the integral of an of t. And what's the integral of an of t at most? 1. So piece 1 is going to be less than or equal to epsilon over 3 times 1. And that's multiplication, not convolution. Now we have pieces 2 and 3. Well, pieces 2 and 3 are essentially the same. So for second and third, well, if we think about what's going on now, how bad could f of x minus t minus f of x be? Well, at most, essentially twice f of x in terms of its maximum value. So if it's a bounded interval, we have some control over that. And so now you might wonder, well, maybe we actually need finiteness over here. So if interval is finite, f of x minus t minus f of x is less than or equal to twice the maximum of all c of f of c in absolute value. And that's going to be less than infinity. That's just some bound. And now we have the integral of an of t. You can put in the absolute values if you want, doesn't matter, over x greater than delta. But we know this goes to 0. So there exists an n naught such that for all n greater than or equal to n naught, this will be less than epsilon over 3. Or, since I'm doing 2 of them at once, I'll do 2 epsilon over 3. I'm sorry?
Now we have 4 epsilon over 3.
No, we don't have 4 epsilon over 3. Because this is integrals 2 and 3, because I did the absolute value of x.
Oh, you combined it.
Right, I combined them. And so when it all comes together, I can hold my head up high as an analyst and say my final expression is less than epsilon. Doesn't really matter, but it's nice to be able to have everything work out at the end of the day. And so it's interesting to think, if we had an infinite interval, what would we need to assume about f to still be okay? So how could we weaken the result? If interval is infinite, okay, if we assume, what about f? F is bounded. That's all we really needed. So in real analysis, and I know we talked about this for those of you who came to the ice cream office hours, we talked about in real analysis, if you remove a condition from a theorem, usually the proof is harder or there's a counterexample. When you look at the proofs, always ask yourself, why do we have those conditions? Where are those conditions used? I deliberately was very vague. I said, f is continuous, and it converges pointwise. I didn't really go into much detail. Then you can start to ask, well, what type of convergence? What do we mean by converges pointwise? I mean, at each point, an star f is converging to f of x. But it may not be, is there some control here that I want all of them to be within epsilon for the same value of n, that if n gets sufficiently large, it is within epsilon no matter which x you look at. And we have that now. If we are looking at a finite interval, then we have uniform convergence, and it's not just pointwise convergence. There is some sufficiently large n, such that if you're at least that large, then you're within epsilon everywhere. So that's worth isolating. If interval is finite, there exists an n naught such that for all n greater than n naught, an star f of x minus f of x is less than epsilon. And of course, this is, given any epsilon, I can find an n naught such that. So we have good convergence everywhere. This is, I know we're a little bit over, I'm going to just finish right here. This is the small little, come on, if you're willing to sacrifice having the nice Fourier series and put in these little weights, I'll give you uniform convergence. Not a big deal, right? I am quite happy to incorporate the small little weights of 1 minus absolute value of n over n if I get uniform convergence out of that. So what we'll see in the next lecture is that by assuming that we are continuous, we had Fejer's theorem. If we assume that we are differentiable, then we can use the Dirichlet kernels and actually get pointwise convergence of the original Fourier series to the function we care about. But if you've done measure theory, and I think some of you are doing it now, the way most measure theory arguments work is the following. Prove it for a characteristic function of a nice interval. Then prove it for a finite collection of characteristic functions. Then prove it for continuous functions which can be approximated by the finite collections, and so on and so on and so on. That you keep working up the space in which you deal with. And so for a lot of things, it's not a big deal to say, oh yeah, my function is continuous and bounded. And then I have a nice result like this. Well, but my function isn't continuous and bounded. Okay, I'll find a continuous and bounded function that's a really good approximation to my function. And then I'll have the result for that. And then I will pass to the function I care about. All right, so this is a good place to stop. Any questions?